Hello, everybody. Mr. Hasty here. Today we're going to be talking about section 12.2, which is changes of states and thermodynamics. We talk about states of matter. The three most common that we experience are solids, liquids, and gases. We all have a general idea of solids, liquids, and gases. Solids have a fixed volume and shape. Liquids have a fixed volume, but not a fixed shape, and gases have neither a fixed volume nor a fixed shape. But what does that mean and why? So let's talk about the particles. We know that things typically transition in our experience. When we think about water, ice is a solid. When it heats up, it becomes a liquid. When it heats up further, it becomes water vapor as a gas. So real quick discussion of what's called the kinetic molecular theory. Kinetic molecular theory. And how this explains that. So the kinetic molecular theory says that all particles are moving. So when you have a solid, they have bonds between the particles that are strong enough that the objects cannot move from their fixed position. The particles can't move. Those particles are vibrating. I can't draw lines that indicate that, but they can't really get out of their position because of the bonding. Now, when it transfers to a liquid, remember what heating up is. Heat is a transfer of thermal energy, specifically in the form of kinetic energy. If those particles start moving enough, with enough energy, they would be able to break away from those bonds. Now, there's still some attractive forces that keep the molecules or the particles close together. Hence why liquids don't suddenly expand outward. They stay in a fixed volume, but they can move around now. They can move around each other because the bonds between them are not strong enough to hold them in position. They have too much energy and too much movement. If we give them even more kinetic energy, remember, temperature is just kinetic energy, and thermal energy is the kinetic energy plus the potential. So once we heat them up enough, their particles are just flying around and expanding outward. The forces holding them together have really no hold over them, so they don't stick together. They just kind of expand and fly all over the place to fit their environment. So that's what the states of matter are. And we're going to talk about a couple major things. We're going to talk about melting and boiling. Boiling is a specific term of vaporizing. So we're also going to briefly discuss freezing and condensing because those do happen, but we're primarily in this chapter going to be talking about melting and boiling. Melting is the process by where you add enough kinetic energy to transfer a solid into a liquid. Boiling or vaporizing is where you add enough kinetic energy to break that apart and turn the liquid into a gas. Freezing and condensing are the opposites, which means those are actually getting rid of thermal energy. So as condensing is going from a gas to a liquid, as that gas gives off its kinetic energy to another source, trying to heat something else up, the vapor starts to form into a liquid. Freezing is when a liquid gives us some of its energy and forms a solid. So they gain energy to melt or boil, and they lose energy to freeze or condensate. So now that we've discussed that, let's get into some technical definitions about the amount of energy it takes to make melting or vaporizing happen. When we talk about heat transfer, we're going to talk about the heat of fusion and the heat of vaporization. So a heat of fusion is the amount of thermal energy necessary to melt 1 kilogram of a substance. So every substance has a different heat of fusion, And you would research these or look these up like you would specific heats for a particular material. So for instance, copper has a heat of fusion of 2.05 times 10 to the fifth joules per kilogram. What that means is for every kilogram of copper, you need to add 2.05 times 10 to the fifth joules to make that melt. So, this is a different source of calculation than what we did with the specific heats. So the formula for this is the amount of heat required to melt it is equal to the mass times the heat of fusion, which again, the heat of fusion is different for every substance, and you just need to look it up. There's a table in the book on page 331, but most often they'll be given in the problems. So heat of vaporization is the amount of thermal energy necessary to vaporize, which means to turn into a gas, 1 kilogram of a substance. Now, the formula for that's going to be the heat for that is the mass times the heat of vaporization. As a comparison, the heat of vaporization for copper is 5.07 times 10 to the sixth joules per kilogram. Now, what's really important to note is that let me be clear here. The amount of heat required to melt it is just to go from, let's say we're talking about ice. The amount of heat it would require to go from 0 degrees Celsius just to being on the other side of 0 degrees Celsius. If here's 0 and here's solid and here's liquid, crossing that barrier is the amount of heat we're taking. So when we talk about heating through a phase change, let's say that we have a substance, we're just going to use water because it's easy. And it starts here. And let's say it's solid, it's frozen, right? Let's say this is the melting point. Let's say this is the boiling point or vaporization point. And let's say we want to figure out how much thermal energy it's going to take to get to here. So there's quite a few calculations that we need to go into this. The first calculation we would need to do is we would need to do the calculation we did in the last section from this point, our starting point, to the melting point. Let's say it's water, so it's 0 degrees Celsius. We would need to use that using the formula that we did the other day using specific heat. Then we would need to add the amount of energy to cross the barrier, which would be our heat of fusion. We'd have to again do the same formula we did to go from the melting point to the vaporization point, 100 degrees Celsius. Figure out how much energy it would take to cross that barrier, and then do another calculation from 100 to whatever our end point was. So we would have to do 5 calculations there. 1, 2, 3, 4, 5, and then add up the energy from all those calculations. So we're going to do a couple examples of that and use that approach. All right. So given a sample of 1.25 kilograms of ice that is negative 10 degrees Celsius, how much heat would it take to reach a temperature of 45 degrees in a liquid state? So let's think about what we're doing here. We are starting at negative 10 degrees Celsius. We are passing 0, which is where it's going to melt. And then we are going up to 45 degrees Celsius. So we're going to have to do 3 separate heat calculations here and add them up. The first heat calculation, we'll call it Q1, is to go from -10 to 0. Then we have to do a special calculation just to pass that barrier. Anytime you change your state, you have to have its own calculation. And then from 0 to 45 is going to be a third calculation. So the first calculation is going to use the formula that we established last time. For a substance in the same state, you use MC delta T. So in this situation, the mass of the ice is 1.25. Now remember, the C stands for specific heat, and the specific heat of ice is different than the specific heat of water, of liquid water. So the specific heat of ice is 2060 joules per kilogram Kelvin. And our delta T, well, going from from -10 to 0 would be 0 minus -10, which of course is +10. When we do that calculation, we get 25,750 joules. Now, the second step, where we have to jump through the barrier, we have to use the formula mass times the heat of fusion. Well, the mass of the water is not going to change. We have 1.25 kilograms. The heat of fusion for water, and it doesn't matter, now heat of fusion, it doesn't matter if it's liquid or ice, the heat of fusion will be the same here. 3.34 times 10 to the 5th joules per kilogram. So we multiply that and we get 417,500 joules. So it takes considerably more energy, like 20 times the energy, probably not that, but close to it, to just cross that barrier as opposed to go from -10 degrees to 0 degrees. All right, so back to this formula, because now we're all liquid. Got to remember, liquid water has a different temperature than, or specific heat than ice does. It's 4,180 joules per kilogram Kelvin. And we're going from 0 to 45, so it's going to be 45 minus 0. And we will get 235,125 joules. Now, the total for this system is going to be the sum of all of those. So 5, 7, 8. Gonna run out of space here, I'm sure. Yeah. 678,375 joules. Now, I wasn't real careful writing this problem with sig figs, so we technically would have 1 sig fig here. I probably would have intended it to be 3. So in that case, we would have 678,000 joules. I just forgot to add my 0.0s onto my temperatures there. All right, next part. How much energy would it take a 5 gram, well, we don't like grams, so we're gonna have to convert that to kilograms. So we're gonna be talking about a mass of 0.00500 gram ice cube to become steam. So let's assume here that we're starting with a 0 degrees Celsius ice cube. So we're just going to start at 0. We're going to become water, and then we're going to become steam at 100 degrees Celsius. So we're going to actually have to do 3 calculations again. Q1 is to break from the ice to the liquid. Then Q2 is going to be the heating up of the liquid from 0 to 100. And then Q3 is going to be the vaporization temperature. So Q1 is equal to the mass times our fusion. Now the heat of fusion is the same one we used before, 3.34 times 10 to the 5th, and we will get 1,670 joules. So the first thing I'd like you to notice, that's a lot smaller than numbers we were working with before, but that's because our sample is so much smaller. The smaller the sample, the less energy it's going to take to make that happen. So that is just the energy to melt the cube. Okay. Now we're going to turn to this formula. Don't know why that's not working right. So this is Q1, Q2, where we do the mass times the specific heat times delta T. So our mass is still 0.00500. Our C in this case would be the specific heat of liquid water, which liquid water is 4,180. Got to be careful there. And then our delta T would be 100 degrees Celsius. And so when we do that, we get 2,090 joules. And finally, we need the heat of vaporization. So the formula there is mass times heat of vaporization. Now, the formula up here was mass times heat of fusion. So the heat of fusion and the heat of vaporization are not the same. The mass would still be the same. But we're going to have to research what the heat of vaporization of water is. It is 2.26 times 10 to the 6th. And we will get 11,300 joules. So just like before, to get our total, we add those up. And if we round appropriately, the only measurement we were given here was to 3 sig figs. So we're going to have 15,100 joules when rounded of total thermal energy there. So the big thing to understand here is when you cross over boundaries of phase changes, you have to account for the added energy that it takes to do so. All right, that's it for today. See you next time.